Have you ever wondered about what lies outside of our solar system? As an astrophysicist, Zoe de Beurs looks to faraway stars to learn about the exoplanets that orbit them. Are they rocky, like Earth, or are they completely different? Let's meet Zoe to learn more.
Hello everyone, I hope you are all as excited as I am to talk to you guys about space today. So my name is Zoe, I am an astrophysicist at MIT, which means that I study all kinds of objects that are in space. In particular, I work on exoplanets and trying to find them using artificial intelligence, and I'm going to explain what all of those words mean today. So first off, what is an exoplanet? So an exoplanet is a planet that is outside of our solar system. For most people, the sun is their favorite star because it keeps us warm, it helps our food grow, it keeps us all alive. However, these planets are orbiting other stars, so stars that you can sometimes see at night, and because they are orbiting other stars, they are called exoplanets. But why do we actually look for these planets? So finding exoplanets beyond Earth can help us answer all kinds of questions. It can help us answer questions like, are there other Earths out there? Are they similar or completely different than our Earth? Do they have life? If yes, what kind of life? If no, why don't they have life? What's different about them? Finding other worlds can also help us place our Earth into context and help us understand how common or maybe how rare we are. Beyond kind of giving this understanding of Earth, looking for exoplanets also has led scientists to finding some of the weirdest, strangest, kind of unimaginable worlds out there. And it has questioned the very way that planets actually form. So looking for exoplanets can help us understand Earth's uniqueness and can help us understand the history of how planets form. Okay, so the mystery of these possible other worlds have really fascinated star watchers since the time of ancient Greece. And the word planet actually comes from the Greek word planetai, which is wanderer, meaning planets are considered wanderers among the stars. And for centuries, the 8 planets that you see here, which are our 8 planets in the solar system, were really the only planets that we knew of. We imagined that there might be more, but we weren't able to find them. However, this started changing about 30 or 40 years ago as astrophysicists developed advanced techniques and technology to be able to find these exoplanets. Okay, but before we dive into how these scientists did this, I have an important question for you all. So I want you to turn to someone next to you or think to yourself about how many planets you think we have found so far. And I'll give you about 10 seconds to do this, so I'll wait. Okay, I hope you were able to share with someone or think to yourself. So we've actually found over 5,000 planets, to be exact, 5,885 planets so far, which is a huge amount of planets, which is really exciting. So this has really been something that we've only been able to do over the last 40 years. So what you can see in this plot that I have for you guys here is the number of planets on the y-axis and the discovery year on the x-axis. So you can see that in 1995, we started really discovering some planets, and then as specific telescopes were launched into space, we saw more and more of them. And all of these planets here are color-coded based on what kind of method of discovery we use to find them. So there's a lot of different ways to find exoplanets. So what are some of those ways? So we can find exoplanets using powerful telescopes. So telescopes can be kind of thought of as like a super powerful eye that helps us see things that are really, really far away in space, like stars, planets, galaxies, all of that exciting stuff. Our eyes usually cannot see these objects because they're so far away and they're not very bright. But telescopes are designed to collect a lot more light than our eyes actually can. And they do this using lenses and mirrors to make things look bigger and brighter, and also by looking at things for a lot longer time than our eyes sometimes can. It's kind of similar to how you might be able to use binoculars, for example, to look at a bird. But instead, telescopes can look at things that are way further away and way fainter or less bright. So here is one of the telescopes that I actually work at. And this telescope is located in the Canary Islands, so it's right off the coast of Northwest Africa. We work at this telescope during the night normally, because it's so bright during the day that we really can't see all the stars in the sky. And so here you can see this telescope, which is called the Harps North Telescope, getting ready for the night. So as it's getting darker, you'll see in a second that it's going to flip around and going to face towards where we want to point it, so which stars we want to look at. So like I said, the telescope is really busy during the night and not really operating or doing anything during the day. And the same applies to me. When I go over there, I'm working all night and I'm sleeping during the day instead. And so one reason that this telescope is in this amazing location in the Canary Islands is because it gives us access to one of the darkest night skies. So this is actually an image I just took with my iPhone, where you can see the Milky Way and you can see all of these stars. And because we can see so many more stars because it's so dark, that also means that we can try to look for more planets. So it's really an amazing place to be. And in addition to it giving us access to one of the darkest skies, we also have some of the best support at the observatory. So that specifically means we have amazing people that help us called Carmen and Gianni. They are telescope operators, and their job is to keep the telescope safe. So the telescope, some of the dangers that can happen is if it's, for example, raining or really strong winds, that can damage the telescope. So their job is making sure that if that happens, we close the telescope, protect it, and then see if the weather improves and then reopen it if possible. We also get to order snacks every night to kind of keep us energetic all night, keep us up, keep us going. And then lastly, we also have some cats that are at the place that we sleep during the day called the Residencia. And all of these things really make it a really fun experience to be there. But okay, so when we're actually there at night, we have to make a schedule of where we look with the telescope. And so here on the left, you can see an example schedule that I'm showing you. And these schedules are made together with a lot of other scientists who spend years figuring out which stars we should look at. Sometimes they use information from other telescopes that tell us that this is going to be a really good star that might have a really interesting planet around it. So my job every night is to decide in which order we look at the stars that they've come up with. And to make adjustments if, like, for example, the weather turns out that we have to close, kind of choosing which stars can we prioritize since we can't look at them all. And so what you can see on this picture on the right here is all of these dots are all different stars that we can see. But in green are the ones that the telescope can automatically detect, and in red on the bottom here are the ones that the telescope is not able to see right now. And the reason for that is because the moon is right here. So this bright region that you see is the moon. And we might think when we look up at night and see the moon, that's not that bright, that's not that crazy. But for us, actually, the moon is so much brighter than most of these stars that we're looking at and is kind of blinding us right nearby. So we don't want to look at these stars when the moon is here. Instead, what I'll do is try to make sure that we look at these stars when the moon has moved across the sky, when those are something we can see again. So that's something that's really important. Here you can kind of see all the different screens that we monitor. We're keeping track of many, many things to try to get the best kind of data and the best science that we can get out of it. So speaking of science, when we actually look at one star, we only look at one star at a time. We don't look at them all at once. And the reason for that is that we really can only look at one at a time with this specific telescope. Some telescopes can look at many at a time, though. And so what we do is we track the star in the sky as it's moving so that we can look at it for 20, 30 minutes at a time and get as much light of it as possible. And when we do that, we take the starlight and we put it through something called a prism, which will split the light into its respective colors or its respective wavelengths. So this is kind of similar to when you see a rainbow in the sky, where in that case, the water droplets from the rain are causing the light to be kind of split into all of its different colors. So once we have all of this starlight in these rainbow colors, we can actually look for signs of planets. So when I'm back in Cambridge at MIT, I'll use my computer and I'll code to understand this data and look for these signs of planets. And in particular, I'm using a very specific method of trying to look for exoplanets. And this method I like to call the wobble method. Some people will also call it the radial velocity method, but I think wobble method sounds a little bit more fun. And so once we've collected the light from the star, split it into its wavelengths, what we can look at is how those colors seem to be shifting back and forth. So the reason for that is that as your planet is orbiting your star here, it's using some of its mass, some of its weight to pull on the star. And as the star is moving around, this is going to make some of the starlight turn redder as it's moving away from you and turn bluer as it's moving towards you. So this is called a stellar wobble. And the kind of strength or like the intensity of that stellar wobble is going to be based on the mass of the planet. So if it's a really heavy planet, it's going to wobble more and that light is going to shift more back and forth. Whereas if it's a very lightweight planet, that effect is going to be a lot smaller. So this is the way that we can tell how heavy a planet is. So this wobble method really allows us to determine the weight of the planet. Why is that important? I'm glad you asked. So what we can see here is if we have two planets that are the same size, we don't necessarily know how much they weigh unless we use this wobble method. So say that this one is a lot lighter, what that might mean is that it's made of different materials than the one on the left that's heavier. So maybe it's made of some heavier materials like iron, but it's mostly made of a lot of gaseous materials like hydrogen and helium, kind of gases. Whereas the planet on the left, that's a lot heavier, might not really have much of an atmosphere and mainly be made of like these heavier materials like iron and rock, silicates, like all of these kind of denser things, similar to like Earth or Mars in our solar system. Okay, so that's why we want to use this method. So like I mentioned, when we are using this wobble method, we're having these shifts to the left and to the right. And in particular, this kind of rainbow that you're seeing, we often will call the average spectrum, which is moving to the left or right. And being able to measure how much it goes to the left or right tells us this mass or this weight of our planets that we want to know. However, we have a problem. And that's that we cannot always tell very well how strong that kind of wobble is. And that's because of something called sunspots. So our sun's surface has kind of these dark regions on it where some of the material is not able to come towards us as much. And these are called sunspots, these dark regions. And they're all over the sun's surface. They change over time. So they're quite hard to predict. And what you'll see on the right here is when one of these sunspots comes into view, it completely changes that shape of that average spectrum we were talking about, that average rainbow. And that makes it really hard to be able to tell whether that average spectrum is moving to the left or to the right or not moving at all. And sometimes we think we see a planet when actually what we're looking at are these sunspots instead. And so this is a big problem. And in particular, the size of these kind of signals is very different from each other. So what I'm showing you in this plot, all these white dots are the kind of strength of the signal of those sunspots. And those are about 5 meter per second signals. So that's about the same speed of some of the fastest runners in the world, like Usain Bolt, for example. Whereas planet signals for an Earth twin planet is going to be this really small line that you see here. And I promise you, there is a wobble there. It's just really, really small. So that's about 0.1 meters per second, which is about the speed of a turtle walking. So it's like we're looking for turtles in the middle of this kind of forest of runners like Usain Bolt, which is a really hard problem. So what we're trying to do is to try to solve this problem using artificial intelligence methods. In particular, we're using something called a neural network. And this is a kind of algorithm that computer scientists sometimes use, and it's been revolutionizing many really complex tasks. And it's kind of considered state of the art or like amazing at shape recognition. And that's why we want to use it. And so here's a little animation that kind of explains how these neural networks work. So in this case, the scientists wanted to train a neural network to distinguish pictures of cats versus dogs. So the neural network is given thousands of images of cats and dogs, and those are fed into some kind of an input layer. And then the activated neurons that you're seeing here will try to learn features and extract properties of those images so that it can finally tell whether it's a cat or a dog image. And so these neural networks are used a lot in science, but also in all kinds of other applications. So some of those applications would be like, for example, the way that you might see artificial intelligence used in daily life. So if you've ever used Apple Siri or Amazon Alexa or Google Home, those are all examples of artificial intelligence. Google Maps also uses AI to try to get you from one location to another location as fast as possible. You might be familiar with ChatGPT, which also uses AI methods, slightly different than neural networks though. But all of these methods can be really helpful for us. But ChatGPT is by no means the only kind of AI that is used. Another form of AI can be used for medicine, for doctors. They can use it to try to look at images of people's lungs to see if someone might have lung cancer and try to detect it early so they can treat people early. Okay, but let's get back to the stars, the planets, all the good stuff. So like I said, our solution is to try to train a neural network. But obviously, if we want to try to find these planets and look at these sunspots, we're not feeding it images of cats and dogs because that won't tell us very much. Instead, we're giving it information about those average spectrums, those rainbows I was showing you. So here what you can see is a real image of the sun with a sunspot on it, so one of these dark regions. And this is what the average spectrum or that average rainbow looks like for this specific image. And then if we have another observation where there are no sunspots, this is what the average spectrum looks like. Not a big difference. But if you subtract this one from the one on the left, you actually get this difference between the two, which does show a signal, and that signal corresponds to that sunspot. And so what we do is we train our neural network to look at these kind of average spectrum that are that difference, and then figure out what the sunspot signal might be. So how well does this work? We actually built our own neural network to do this using our computer, using code. And what you're seeing here is the neural network in action. So the neural network has certain things that it sees, those average spectra, and then it's predicting immediately what the sunspot signal is. And so it does this really accurately, and that's really exciting because this means that we're able to now find planet signals that are 2 or 3 times as small. So these signals were previously hidden and we really couldn't see them. And so what does this mean and what have we been able to do with this? So with these AI methods, we were able to measure the masses of 3 planets. So these are the 3 planets. They have kind of a funny naming system. So K2-167 is one of them. The name means that it was discovered by the Kepler-2 mission. So it's like a extended mission of Kepler. And then the number is just the 167th object that mission saw, that telescope saw. And then the B usually means it's the first planet that you see. So C would be like the second planet, D would be the third planet. But this planet in particular is a little bit smaller than Neptune. And we didn't actually know what kind of planet it was before. Kepler 538b is more of like kind of a terrestrial rocky planet, so more similar to like Earth and Mars. And then K22b is also a planet that's slightly smaller than Neptune, so it has a little bit of an atmosphere. But this was really exciting. We didn't know what kind of planets these were before, and we're excited to keep doing this. So the next thing is really that I'm going to be applying these AI methods that I helped develop to a gold mine of data for dozens of stars. And we expect that we'll measure the masses or the weights of some already known planets where we just don't know what they're made of, but we know they exist. And then we can find out whether they are rocky or gaseous planets. And lastly, but not leastly, we expect to find many new planets as well with this method. So planets that we didn't even know existed, and we're really excited about this. Okay, I hope that you guys are a little bit excited about planets after I told you all about this stuff. But I also want to talk to you guys a little bit about something entirely different. So I want to talk to you guys about some of the things I enjoy doing when I'm not doing science. I also really love being active. I love moving. So here's me and my brother right before we ran a really long distance, a half marathon. Here are some of my friends at MIT at the MIT ice rink going ice skating. We all usually go on Fridays. I also love fresh cut flowers. I love rowing. So there's a river right by MIT that I like to row on with friends. I enjoy hiking. I also love animals. So here I'm being trampled by one of my friends' dog, Vala. But I just want to kind of show you guys that scientists do many things in addition to science, and we can have hobbies, we can have other interests, and that's totally fine. Um, I also want to emphasize that my kind of own path towards science was pretty nonlinear. I didn't necessarily immediately know I wanted to be a scientist as a kid. Instead, I actually really loved animals and I thought I was going to be a farmer. Thought I was going to have pigs and cows and all that good stuff. And then when I got a little bit older, I really enjoyed art. So here I am painting my brother's face, and I thought I was going to be a painter when I grew up. And then later on in high school, I kind of found other creative outlets. I started doing a lot of film. So here I'm filming a football game. I also really loved chemistry. So I have a bunch of rainbow test tubes here. And it really wasn't until college that I kind of discovered astronomy and astrophysics. I mean, even then, I kind of switched my major 3 times and it took me a while to figure it out. So I just want to emphasize to you all, if you're not sure if you want to do science or if you have a lot of other interests, that's totally fine. Everyone is welcome and you don't have to know immediately. Okay, and then the other thing I want to say is that you can also combine some of your interests. So I combine some of my interests in science and art, and I have here a painting that I made of the telescope that I work at, as well as a painting that I made of some of the kind of rainbow spectra that you're seeing in some of the earlier slides. Okay, so the takeaways for today's talks. One, planets are awesome. I hope I convinced you of that. They can help us understand our Earth and the solar system. These powerful telescopes can allow us to find exoplanets and understand what they're made of. Artificial intelligence can help us discover new worlds. And most importantly, science is for everyone, from animal lovers to athletes to artists. Everyone is welcome and can contribute to science. So if you are interested in contributing to science, please feel free to scan this QR code, where you can join a community of people who are helping to identify signals, from things like black holes to planets to all kinds of other cool astrophysics. Thank you so much, and I'm excited to hear all of your great questions.
Thank you so much, Zoe. That was an incredible presentation. While our Nord Anglia students are still filling in some questions into the chat, I wanted to start with what is behind you. Now, is that the telescope that you worked at?
Yeah, it's a great question. Yeah, so this is the telescope that I worked at in the Canary Islands, and I got to spend about a week and a half there last year in January. But yes, this is the telescope that's right there. Yeah.
And why are some of these telescopes so high up? Because I see those clouds right behind you also.
Yes, yeah, no, that's a great question. So we are above the clouds here, as you can see. And so the reason for that is that we want to put the telescopes often above the atmosphere, above the clouds, because the clouds themselves can kind of cause like some noise or can make it harder to see the stars. So they can make it harder for the light to reach us directly. So we usually want to be like as high as possible, and we also want to be in a place that's like really dry, so where there's not a lot of like humidity, not a lot of water vapor. But yes, that's really important. So there's some telescopes that are also in deserts and stuff like that. Yes.
I can think of another place that's really high up that also has low humidity. They're telescopes in space, right?
Yes, that's a great question. That's a great point. Yes. So yeah, a lot of telescopes are put in space so that you can avoid this problem altogether. You don't have an atmosphere you have to look at. And the other really great benefit is that you can look all day and all night because we're not, bound to a planet that is going to be facing the sun sometimes. Instead, you can have it always be facing away from the sun. So we can like be taking all these amazing observations and data of stars or galaxies all day and all night. But there are reasons why sometimes we put telescopes on the ground as well. Sometimes it can allow us to have a lot more control over the telescope, or it can make it really stable. So there's kind of a place for both kinds of telescopes.
Got it. Thank you, Zoe. So, speaking of using these data that you're gathering from the telescopes, Lynn is wondering, in addition to helping find, the sunspots, how will AI change finding planets in the future?
Yeah, Lynn, that's a great question. In addition to looking for kind of these sunspots, there's been a lot of cases where AI has also been used to look for kind of planet signals that are hard to find, like kind of looking for needles in a haystack. Some telescopes, the ones in space, will actually look for a completely different phenomenon where the planet kind of goes in front of the star and blocks some of the light. And so AI methods have been used to try to find some of these really subtle signals. And in addition, one other example, something that I've been working on as well, is there's a new telescope going to be coming online called the Roman Space Telescope that's going to be looking for planets that are much further out and much smaller, so more Earth-like generally, or more terrestrial. And AI is going to play a really important role there because there's such a huge amount of data that no human astronomer can look at all of it at the same time. So AI can kind of do it a lot faster and more automatically. But that's a great question, Lynn.
That actually is a great transition into our next question from Rachel. So, you've mentioned this really powerful Roman space telescope that's in the works. And Rachel's wondering, what is the most powerful telescope in the world currently?
Oh, that's a tough question, Rachel. Hmm. I feel like this is hard to answer because it depends a little bit on what you want to do with the telescope. So like, each telescope kind of has like its unique like strengths and weaknesses. So it's hard to say like one singular telescope that is like the strongest, the best. But of course I'm a little bit biased. I'm gonna like the telescopes that are the best for the planets. So I would say that probably for finding planets and trying to figure out like whether they might have like an atmosphere, kind of like Earth has an atmosphere. I would say that the James Webb Space Telescope is probably the most powerful one. So this one only launched, I think, 2 years ago now, and has already like made these huge, exciting discoveries. But yeah, I think it really depends on what you want to do, which telescope is the best one. But thank you for that question.
Got it. And now we have a question from Naomi who's wondering, what's the most exciting discovery you've had during one of your night shifts?
Oh, that's a good question. Um, hmm. I guess so. I guess the maybe something that's important to mention is when I'm taking these observations, I'm like contributing to a large database. And so, some kinds of astrophysics, you take data on one night and you immediately know exactly like what you're looking at, or you might have kind of taken all the data you need to make a discovery. But with this exoplanet science, you usually have to look at a star for like months, if not years at a time, before you can kind of figure out how much it weighs. So I think that on a given night, I might not make an amazing discovery necessarily, but it is just really fun to kind of be at the telescope. And I've also really enjoyed just kind of going outside and enjoying the night sky myself. So I think that's probably the most fun part, but that's a really good question, Naomi.
Yoga's wondering, have you used space telescope data and have you used your AI methods to help interpret that data before?
Yeah. So the name was Yogi, or yes, okay.
Yeah.
Yeah, so Yogi, so I have used data from a bunch of telescopes that are in Korea before. So this was on a completely different project, but and this is a telescope network that looks for these kind of planets similar to the ones that Roman is going to look at. So yeah, I have used data from space before. I've also used data from the TESS mission before and the Kepler mission. So a lot of the time we're using data from multiple telescopes to make a scientific discovery. But yes, great.
Got it. Luke is wondering if you could use AI to answer any big questions about the universe that still puzzles you. What would it be? What questions are you dying to know the answers to?
Okay, that's a good question, Luke. I personally think that I would like to try to use it to kind of find exoplanets that you don't even think could exist. So sometimes when, we're looking for these signals, we're kind of looking for things that are familiar to us, because it's easier to recognize and it's a lot easier to find. But I think I would be most interested in kind of like finding planets that you don't even think could exist. So like, for example, planets that are so heavy that they might be made of like almost completely like lava, so like these lava worlds, or planets that are not in kind of a circular orbit, but planets that are in like an elliptical orbit, and that are kind of going in such an elliptical orbit that you wouldn't even think that this planet could be stable and could be that way. So I think it would be really cool if we can use AI methods like for something called anomaly detection often. So like looking for things that are unexpected or not explained. So yeah, but that's a great question, Luke.
That leads perfectly into our next question from Rachel, actually. So Rachel's wondering, do you have any favorite exoplanets that have been discovered? Because Rachel says that she's heard of planets that have strange atmospheres or even rain diamonds.
Ooh, that's cool. I'm wondering which planet you're thinking of, Rachel. Yeah, I think some of my favorite planets would probably be a planet called Hat P2, Hat P2b. So this is a planet that is about 9 times as massive as Jupiter. So it's a very big planet. But instead of it taking hundreds of days to go around its star, it only takes about 5 days to go around. So it's going really fast around the star, and it's going on a very like elliptical orbit. So again, like not a circular one. And so what this means is that this planet is getting really hot when it gets close to its star, and then really cool again when it gets far away. So it's a really crazy system, and it's still something where we don't really understand how it formed that way, how it got there. And there's just like so many cool questions you can ask about it. But yeah, so many cool planets out there, so many crazy ones.
Yeah, and now that leads to another question from Shohan, and Shohan's wondering, have you ever found a new planet by yourself so far in your research?
I wish, but that's a good question. But yeah, so not yet. So I think right now I've mainly kind of looked at planets where we didn't know something about them, and I was able to kind of give new facts about them or contribute new knowledge about them, but not necessarily finding an entirely new planet from scratch. But that is what we're working on next. So like these methods will help do that. We're just not quite there yet, but we're gonna get there.
Oh, I have full faith you're going to get there for sure. And then I want to ask one more science question, then transition into talking about your educational journey that you ended your talk with. But before we do that, Lynn is wondering, could you walk us through how planets are named and who actually names them?
Yes, that's a great question, Lynn. So I wish that we could just name them ourselves sometimes, honestly. But the way that it works is that typically it'll be named after like which space telescope or which telescope first finds. It doesn't have to be a space telescope. Which telescope first finds the planet. So in some of the examples I was showing you, it was, for example, like Kepler, or sometimes it's also called like the HAT P2 example I was talking about. So like for the HAT P2 one, it's coming from the HATNet survey, it's a telescope survey. And then the two is usually like the number that you see is the like first planet or the second planet in this case. So it's very systematic. Like it's the telescope name, how manyth planet it found, and then the BCD is based on like how we think that it might be in its orbit. So A is skipped because A is the star. So, and then the first planet is B, the second planet is C, the third planet is D. Sometimes, however, we find a planet later on and realize that we accidentally skipped one. So it is possible that it ends up being like planet E is the first one, planet B is the second one, et cetera, et cetera. But that's a great question. Sometimes planets also get nicknames, but they don't always stick. So it kind of depends.
That's really cool. I'm so curious about those nicknames, but in the interest of time, I'm going to ask you some questions about your journey now. And so, we're wondering, what is the best class that you took in high school that, you use or employ in your work today? What helped get you here?
Oh, that's a good question. I think. In high school, I actually didn't really take a lot of astronomy classes or anything like that. But I think some of my physics classes were definitely helpful in kind of building intuition. A lot of astronomy and astrophysics is actually physics and math. So I would say probably kind of like calculus classes or yeah, or like introductory physics classes. I think if I could have gone back to high school, I think something that would have been very helpful is taking some coding classes. I did not do that, but that's also a skill that you use a lot as an astronomer or astrophysicist.
And so did you end up learning? So when you say coding, you're referring to taking like computer science courses, right? And is that something that you were introduced to in college?
Yeah, so I took only one computer science class in college and mostly just learned how to code with the projects I was working on or with the research I was working on and kind of taught myself. But I think it is really helpful to take computer science classes. It makes you just better at most things that might be relevant. Yeah.
I fully agree with you. I wish I took those classes in high school as well. Now we have a question from Dan, and Dan's wondering what made you decide to become a scientist specifically focused on exoplanets? When did this happen?
Yeah, that's a good question, Dan. So when I was in college, I did a whole bunch of different research projects. I like worked on kind of like a atomic physics microscope for a while, and I enjoyed that a lot. Then I did a project where I was looking at really high energy particles that come out of space. And when I did that, I kind of realized I really enjoyed like using computer science and using coding. So I kind of in my like second year of undergrad reached out to someone who was using these AI methods for some kind of astrophysics, and they happened to be working on exoplanets. And so it was kind of like by coincidence, honestly, that I started working on these exoplanet projects. But I just really fell in love with it and loved kind of like just the day-to-day coding and the data analysis. So I think I'm someone who also just loves all kinds of astronomy and astrophysics. Like I love talking about black holes too. I know some people kind of pick their favorites and stick with it, but I think I kind of enjoy a lot of different things. So I kind of found this by just trying a bunch of things and eventually kind of landed here. So I would definitely encourage you to just try a whole bunch of things and see what might interest you.
I like that idea. And speaking of trying things, Lynn is wondering if I want to look at planets or stars myself, well, where do I start? What can I do?
Yeah, that's a great question. So I mentioned at the very end of the talk, Lynn, that there's this Zooniverse project. And so there are some like data from planets that you can look at, and you can learn how to recognize those planet signals yourself. So maybe we can send a specific link to Lynn afterwards as well. But if you would like to learn kind of what do these signals look like and can I play with this data myself, I think Zooniverse is a really good place to start.
Fantastic. And now, before we close, I want to ask you one more question, Zoe. So, we're wondering, you've mentioned all of this amazing science you do, the travel you do, the coding you do, but you also told us about how you row and run and have time to play with dogs and skate. How do you manage your time to be able to balance all of these things?
That's a good question, Fatima. I mean, honestly, I think it's hard to balance your time and do all of these things, but I feel like it's just so important that we make time for friends and fun things and kind of relaxing that I feel like if I can spend a little bit more time like exercising or with friends, it just makes me like a better person and a more productive person too and like more balanced. So I think it's hard, but I think it's really important to make time for that kind of thing. I also drink a lot of coffee. I think that that helps too.
I think those are two really insightful pieces of information there. And I think you're right. It's always, I mean, even that is still a journey in itself, figuring out how to balance these things. And with folks like us and the Nord Anglia students on the call, we have so many interests. It's not possible to pursue all of them simultaneously, but we will find a way. And with that, I want to share with folks really quickly. I hope you'll also join us next time to learn about plasmas in the wild. That's going to be really exciting. And with that, I just want to thank everyone for joining us today. I want to thank the MIT Nord Anglia Education Collaboration for making this series possible. I want to thank students and teachers for asking such wonderful questions and for tuning in with us today. And lastly, I want to thank Zoe so much for her time and insights. It was really a pleasure, Zoe. Thank you so much.
Thank you guys.
All right, with that, goodbye, everyone. See you next time.